The DARPA Logger program aims to advance learning algorithms in off-road robotics. The main challenge in off-road robotics is the highly changing and unstructured environment. Learning algorithms can adapt to changes in lighting conditions and obstacles' appearance, where conventional algorithms often fail. The Logger vehicle provided by NREC comes with 4 cameras allowing passive stereo vision, a GPS receiver used to reach a GPS goal, and 4 onboard computers. Stereo vision is typically reliable only up to about 12 meters. Increasing this range with passive vision remains highly challenging. A short-sighted robot makes poor decisions and will get stuck in cul-de-sacs. NetScale Technologies and New York University have focused their effort on developing machine learning techniques for long-range vision along with a robust and collision-free software navigation platform. This long-range vision system increases the vision range of the robot to 50 or even 100 meters or more. The robot first finds the horizon using a ground plane extracted from stereo points. It then builds a series of normalized image bands at different distances so that it can train on and classify objects of all sizes. The convolutional neural network is trained both offline and online using the short-range stereo labels such as traversable and obstacle to learn the appearance of natural obstacles, which are then classified in the long-range patches of the image. This technique has been dubbed near to far learning. Convolutional neural networks are particularly well suited for extracting features from images while providing scale and translation invariance. 2 layers of convolutions separated by a max pooling layer produce a 100-dimensional feature vector for each point in the image bands. The feature extractor is trained offline using logs captured during the full duration of the program. The online logistic regression classifier identifies the features as traversable and obstacle and constantly updates the classification of distant patches based on the labels produced by the stereo in the near range. The labels are organized in a hyperbolic polar map, which is an efficient pseudo-image space representation whose resolution drops off with distance, thus fitting the inherent range uncertainty of long-range vision, and providing an appropriate space for mapping and planning. On the left is the hyperbolic polar cost map, and on the right the RGB information. As the long-range vision requires heavy processing, a multi-layer perception and planning architecture guarantees a high reactivity while the robot thinks about long-term decisions. On the right, an independent, fast, and short-range vision system detects obstacles in real time and avoids all collisions. Another key module is the rotational visual odometry, which corrects the unreliable positioning system using vision at very low computational cost compared to traditional methods. In this aerial view, the non-visually corrected poses in black and green use only odometers, IMU and GPS, but both are incorrect. A traditional full visual odometry system outputs the slightly incorrect red curve, which is of comparable accuracy to our hybrid visual odometry in blue, but is significantly slower. Another key component that makes our robot smoothly avoid all obstacles is the cheap and efficient trajectory recording module. Our robot models its dynamics by recording a set of possible trajectories into a bank, which you see here. When running, the robot queries the trajectory bank to know what it can do based on its current wheel speeds and selects the best trajectory given the current cost map. After a few hours of human or self-supervised driving, the robot knows what trajectories are possible and navigates smoothly around obstacles. It can even learn new trajectories and improve by itself. This very simple technique requires minimal engineering effort, but is capable of modeling complicated trajectories. It completely bypasses the need for traditional complex parameter identification and tuning. To conclude, the NetScale NYU system has proven its long-range capabilities in various government tests and numerous non-official tests, thanks to machine learning and a solid, efficient software navigation platform.